Hi children and viewers. In previous video I explained about the series combination of capacitors, how the capacitors can be connected in series and when we can use the series combination. I explained in detail in the previous video. I will give link of that previous video in this description, so you must watch it. So in this video I am going to explain about the parallel combination of capacitors. So here first thing is, in this video you are going to learn about this one and how we can derive the expression for equivalent capacitance and how the charge can be moved in the parallel combination. These 3 points you are going to learn. First thing is, what is meant by parallel combination of capacitors. So I already explained here. This is a one capacitor. In that, this one can be taken as first plate and this is taken as second plate. Clear? Now this is the another capacitor. Again this one is first one and this one is second plate, and this is the another capacitor. Again this one is first plate and this one is second plate. First the capacitor should be arranged in parallel like this. After that, all the first plates of the all capacitors given to one point. Clear? This is the first capacitor, second capacitor, third capacitor. First plate of the first capacitor, first plate of the second capacitor and first plate of the third capacitor, all are given to the one point. They are given here 1 point. Clear? Similarly, second plate of the first capacitor, second plate of the second capacitor and second plate of third capacitor, they are also given to 1 point. They are given to 1 point. Now this is the 1 point. For example, I am saying this is now A and this is B. Clear? All the first plates are given to the point A, all the second plates are given to the point B. Now in between these two, one battery is connected. Across these plates, one battery is connected. That is called here parallel combination of capacitors. First, all the capacitors should be arranged in a line like parallel. After that, all the first plates are given to 1 point and all the second plates of all capacitors given to 1 point. Across these 2 points, we have to give one battery. This type of arrangement of capacitors is known as parallel combination of capacitors. Clear, children? So this is a just arrangement of parallel combination of capacitors. So here in parallel combination, you have to observe which quantity is constant and which can varies. So we know that C is equals to Q by V. C is equals to Q by V. In series combination, what we discussed, in series combination, the charge is moving in only one path and the potential can varies across every capacitor. The capacitor C1 is having potential V1. Capacitor of capacitance C2 has potential V2. And C3 like V3. That means in series combination the potential can varies from one capacitor to the another. One capacitor to the another and charge remains constant. So in this also, here two quantities are remains constant. Let us discuss which one is constant and which can varies. Clear? And now look at this diagram. Here it is given to battery. So the positive, all the first plates are given to 1 point. That point is given to the positive. That's why here the charge accumulate on every capacitor. First one is taken as positive. Clear? So that's why here I am writing plus Q1 plus Q2 plus Q3 like that. Here all seconds are given to the minus. That's why here we are showing that minus Q1 minus Q2 minus Q3. Clear? So plus Q1 plus Q2 plus Q3 and minus Q1 minus Q2 minus Q3. That means what we are saying about that charge is Q1, Q2, Q3 like that. The charge supplied by the battery is here now Q. Clear? The charge supplied by the battery is what? Plus Q. That should be splits into like 3 paths. In series combination, the charge can move in only one path. We discussed very clearly there. In series combination, the charge is moving in only one path. But in this case, the charge is divided into number of paths. That means the charge is moving in number of paths. Here we have 3 capacitors. That's why it is written as Q1, Q2, Q3 like that. If you can take a number of capacitors like Q1, Q2, Q3 and so on Qn. That means the charge supplied by the battery that should be distributed to the all capacitors in different paths. In series combination, the charge supplied by the battery that should be sent to the all capacitors in one path. Clear? In series combination, for example here I am drawing here, this is the first capacitor, second, third like this. So all are connected in series now here. What I am telling, the charge is distributed to the all capacitors in one path. This is the series combination diagram. So I clearly explained in the previous video. That's why you have to, in this video you have to simply remind that in series combination the charge is moving in only one path. In this case the charge is varies from one capacitor to the another capacitor. That is the first important thing you have to remember. Clear? And second thing, in this case here the capacitors should be here now in parallel to the battery. How they are? In parallel to the battery. And now in this case the potential difference across every capacitor V1, V2 and V3 and V. Clear? The potential across the battery is V and the potential across is here V1. Across the second capacitor is V2 and this one is V3. In parallel combination, you have to remember one more thing here, that is important. Here V1 is equals to V2 is equals to V3 is equals to V. Clear? Because every all first plates given to 1 point and all are given to the all second plates are given to the negative. That means here at this point, in between these 2 points only some potential is there. That potential is equally shared to the every capacitor. Simply children, you have to remember that in parallel combination the capacitor potential should be equals to the applied potential. And the charge supplied by the battery that should be distributed to the all capacitors in different paths. You have to remember that. That's the important thing here you have to remember. So that's why here you have to remember like this. In parallel combination, simply here you have to write Q is equals to Q1 plus Q2 plus Q3. This is equation number 1. Q is equals to Q1 plus Q2 plus Q3. What is Q? Charge supplied by the battery. Here that should be taken as Q, that should be equals to the sum of charges across the all capacitors Q1, Q2, Q3. So I will explain in detail this one. And next thing here, what I told you up to now, in potential V1 is equals to V2 is equals to V3 is equals to V. This is the second important point. The potential across every capacitor should be equals to the potential applied by the battery. That's the point you have to remember. And now in this case, now I am going to say how the charge can be induced, how the charge can move in the parallel combination. I will clearly explain here. First you have to watch the diagram carefully. So here this is the capacitor of capacitance C1, and this is the capacitor of capacitance C2, and this is the capacitor of capacitance C3. Clear? Here I am showing separately here. This is the first capacitor. Just I want to say what's happening there. Just imagine. So this is the first capacitor. The charge is supplying is Q. Here how much is charge is going to the first capacitor? Q1. How much is going? Q1. That means on first plate what it reaches? Q1 can reaches the first one. Clear? From this battery Q charge is moving, and that charge is moving like this. At this point some amount of charge is moving like this. That is how much? Q1. That will reaches the first plate plus Q1. After that, here the first plate and second plate separated by some distance. Here when there is some positive charge on the first plate, due to the induction, inside of the plate, second plate, some Q1 charge is developed. In addition to that, outside what you have to say, plus Q1 is developed. Clear? Q1 amount of charge is supplied to the first plate, that is Q1. Due to this amount of charge, some negative charge is induced on the second plate. Negative charge is induced on the second plate, that is taken as minus Q1. That minus Q1 is inside the capacitor, inner surface of the capacitor, and again due to that some plus Q1 charge is induced outside the second capacitor, second plate. So like that is I am showing here the Q charge is reaches at this point. At this point here the charge is Q, that should be split into like Q1, Q2, Q3. At this point charge is Q, that should be split into the Q1, Q2, Q3. Here when the Q1 reaches the positive first plate, the Q1 is charge of first plate. Due to this what I am telling here, minus Q1 is induced. And after that outer surface on that what you have, Q1 is there. That Q1 is again supplied like this. That should be moves like that. Clear? And after that I am going to explain for second one. At this point some part of energy is supplied to the Q2. That Q2 is reaches the first plate. That's why here I am writing plus Q2. Due to this plus Q2, here minus Q2 is induced inside the second plate, and outside the second plate of the capacitor plus Q2 is induced, and that plus Q2 is sends like this. And similarly we can observe same thing in this case. Here the Q is again, there should be some part of energy is charge is what it is Q3. Again here what you have to say, plus Q3 is reaches the first plate of the third capacitor. Due to that what you have to say, minus Q3 is induced. Minus Q3 is induced. And outside what you can expect, plus Q3. This plus Q3 is again going like this. Clear? Again this Q1, Q2, Q3 reaches this point. At this point again what rate according to Kirchhoff's laws? Yes, Q1, Q2, Q3 are enter into the junction. The amount of charge enter into the junction equals to the amount of charge leaving. That's why here what right? Q is equals to Q1 plus Q2 plus Q3, and again that should be goes to the like this. So here also same thing. At this point what you have to say, Q is divided into Q1 plus Q2 plus Q3. So in this way, the charge can be distributed in the parallel combination of capacitors. Very simple. What I explained in series combination, that is the same thing. On first plate, the positive charge will be induced. Due to that, some negative charge is induced on the second plate of the capacitor inside. Again, due to that, the same amount of positive charge should be developed on the another side of the second plate of capacitor. Clear? So in this way, here simply we have to go for distribution of charge. Actually, during the IPE examination, no need to mention distribution of charges, all these things. Simply what I draw first, you have to go for the diagram and directly go for derivation. Clear? So here, to understand very deeply, I am going to explain that much of distribution of charge. Clear? And now here over, what's that? Already we are taking capacitors, they should be connected in parallel, and how the charge is distributed on every capacitor we discussed. Now we can go for effective capacitance of the capacitors. Effective capacitance of the capacitors in this combination. We are going to go for derivation for now. So for that, here what you have condition, Q is equals to Q1 plus Q2 plus Q3. Q is equals to Q1 plus Q2 plus Q3. The entire thing should be here, I am explaining like this. This is a capacitor of resultant of capacitance C. Clear? And that should be given in parallel to this one. And now potential is what here? V. Applied potential is nothing but, this is the what? Applied potential. Applied potential, that means equivalent potential or resultant potential, and C is what? Equivalent capacitance. And what is the charge supplied? Q. So that means here C is the equivalent capacitance and Q is the amount of charge supplied and V is the amount of potential applied. That should be nothing but equivalent potential. Then what we write? Now I will write here equivalent capacitance can be written as capacitance. How we can write? C is equals to Q by V. In this entire configuration, we are getting C is equals to Q by V. For that, from that formula, we will write C is equals to what you have? Q by V. C is equals to Q by V. From that formula, I am writing now Q is equals to CV. Q is equals to CV. And now similarly, for first capacitor, according to this formula, what we write? What is the amount of charge on the first capacitor? Q1. Q1 is the amount of charge on the first capacitor. Then here Q1 is equals to Q is equals to CV. Then what do you write? Q1 is equals to C1 V1. And similarly for now, second capacitor, Q2 is equals to what? C2 V2. And now for third capacitor, Q3 is equals to C3 V3. Clear? So now substitute these values Q1, Q2, Q3 values in equation number 1. I am substituting there. Q means what? CV. Q1 means what? C1 V1. Q2 means what? C2 V2. Q3 means what? C3 V3. Substitute there. Then CV is equals to C1 V1 plus C2 V2 plus C3 V3. C3 V3. So again what I told you, in parallel combination V1 is equals to V2 is equal to V3 is equals to V. That's why simply I am writing CV is equals to C1V plus C2V plus C3V. Then what you have to write? CV is equals to V into C1 plus C2 plus C3. Clear? So here what you have to say, V cancel, then what you get, C is equals to C1 plus C2 plus C3. So this is the expression for effective capacitance. Effective capacitance, C is equals to C1 plus C2 plus C3. If the circuit has n number of capacitors, I will write like this, C is equals to C1 plus C2 plus C3 plus and so on Cn. This is the expression for effective capacitance in parallel combination. Effective capacitance in parallel combination. Children, what we got in series combination of capacitors, 1 by C is equals to 1 by C1 plus 1 by C2 plus 1 by C3 plus and so on. And now C is equals to C1 plus C2 plus C3. It means that from this equation what you have to say? From this equation what you have to conclude? While we have in parallel combination, the equivalent capacitance is nothing but sum of the all individual capacitances of capacitors. The algebraic sum of capacitances of capacitors is equals to equivalent capacitance or resultant capacitance. So children, this is simply about the parallel combination of capacitors. Let us see here, children. Again, this is the way, children, one of the most important topic, that's why you have to watch carefully. So here, children, see once again, we have three capacitors are there. They have capacitances C1, C2, C3. Here they are arranged in parallel like this. First plates are given to one point, second plates are given to the another point. Across these 2 points we are giving some battery. That should be shown like this. In this case, the amount of charge supplied by the battery should be split into 3 ways because we are taking 3 capacitors. If we can take 4 capacitors, 4 paths. If we can take 5 paths. Like that, here the charge supplied to the first one is Q1, next one is Q2, next one is Q3. So, according to the Kirchhoff law, what right? The amount of charge entered into the junction equals to the amount of charge leaving the junction. That's why what right? Q is equals to Q1 plus Q2 plus Q3. Clear? And after that, here we have another condition is there. Here all plates are given to one point and all second plates are given to the another point. In between these 2 points, some battery is connected. That's why the potential across every capacitor is same as applied potential. Here what we consider, V1 is the potential across the first one and V2 is the potential across the second one and V3 is the potential across the third one and V is the potential across the battery. That's why in this combination here V1 is equals to V2 is equals to V3 is equals to V. Clear? After that, here equivalent capacitance can be written as C is equals to Q by V. Here Q is total amount of charge what we supply and V is the total potential what we applied. That's why here from the what we get Q is equals to CV. Q is equals to CV. Then here according to that we can write Q1 is equals to what? C1 V1 and Q2 is equals to C2 V2 and for third capacitor Q3 is equals to C3 V3. And after that we are substituting all these values in equation number 1. Then what do we get? CV is equals to C1 V1 plus C2 V2 plus C3 V3. And what you have condition equation number 2, what is that? From equation number 2, V1 is equals to V and V2 is equals to V and V3 is equals to V. From that what we get? CV is equals to C1V plus C2V plus C3V. Then here VV gets cancelled. Then what we get? C is equals to C1 plus C2 plus C3. So here C is equals to C1 plus C2 plus C3. Here if you can consider n number of plates, then what we write? C is equals to C1 plus C2 plus C3 plus and so on Cn. From that equation, what you have to conclude? The equivalent capacitance is nothing but it is the algebraic sum of individual capacitance values of all capacitors. And children, here you have to remind some important points here. So here, in parallel combination, here you have C is equals to C1 plus C2 plus and so on Cn. Clear? In parallel combination, the effective capacitance is always higher than the highest value of capacitance of a capacitor in that combination. Clear? The equivalent capacitance of a capacitor, parallel combination capacitors, is always greater than the highest value of capacitance of capacitor in that particular combination. So for example, here I am taking C1 is 2 and 2 farads or microfarads, anything, and C2 is equals to 4 microfarads and C3 is equals to 6 microfarads. Clear? Then what is the equivalent? C is equals to what, right? 2 plus 4 plus 6. 6 plus 6, 12. 12 microfarads. So here the C value is greater than now C3, because among 2, 4, 6, C is greater. C3 is 6 and C is 12. 12 is always greater than 6. That's why here C is greater than C3. That is the one important point you have to remind, because during the problems and any competitive exams you have to observe that one. Very simple. The highest value of a capacitor is 6 microfarads in this case. That should be very less compared to the equivalent capacitance. That is the first thing here. And second thing is, C is equals to 1 by C1, sorry, C is equals to C1 plus C2 plus and so on Cn. Then here we will take C1 is equals to C2 is equals to C3 is equal and so on, that is equals to C. That means all capacitors have equal capacitance value. All capacitors have equal capacitance value. Then what do you write? C effective or equivalent is equals to C plus C plus C plus and so on. How many times? N times. Then what do you get? C effective is equals to what do you get? NC. C effective is equals to NC. Clear? So this is the another important point. In series combination, what you have? 1 by C is equals to 1 by C1 plus 1 by C2 plus and so on, like that. The question should be like this: find the ratio of equivalent capacitance in series to the parallel. In series to the parallel asked. And how we can find? Already in parallel what you have? C effective is NC. Then series what it is? C series I am writing S. Here what write? 1 by C plus 1 by C plus 1 by C. That means how many times? N times. Then what you get? 1 by CS is equals to N by C. N by C. From that what write? CS is equals to C by N. CS is equals to C by N. So what you have to find? Ratio. Here CP by CS. CP by CS. What is the CP value here? NC. And what is the CS value there? C by N. Or like CS by CP also you have to write. Depend upon the question. Depend upon the question. In this case I am writing here NC is equals to N by C, like that. So here you have to find out all these values should be like that. So depend upon the situation. Depend upon the situation. So children, this is the complete information about the parallel combination of capacitors. Generally, when the parallel combination is required means where we require more amount of storage of charges. Clear? When we require more amount of charge to store, then the parallel combination of capacitors should be preferable. That's why here children, so this is the complete information about the parallel combination of capacitors. So I hope you understand. If you can understand this one, like, share, comment the video and subscribe my channel for latest notifications. Thank you children. I hope you understand. So we will meet in the next video with some other interesting topic. Bye. Take care.